Tonight, we're going to find out how long it would actually take to reach the nearest stars. The ones close enough that we've named them, studied them, and confirmed planets around some of them. And every plan, every dream, every proposal humanity has ever drawn up for getting there runs into the same problem. Because how long it takes isn't a single answer. It changes entirely depending on which propulsion system you put behind it, and some of those answers look nothing like what you'd expect. By the end of tonight, you're going to know exactly where our nearest stellar neighbors sit, what every serious propulsion concept delivers against those distances, and what it would actually take, in physics and engineering, to reach any of them within a human lifetime. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand everything that follows, you need to understand what a light year is. Light is the fastest thing in the universe, moving at 186,000 miles per second. At that speed, it covers the 93 million miles between the Sun and Earth in 8 minutes and crosses our entire solar system in under 6 hours. A light year is how far light travels in one full year. At that speed, roughly 5.88 trillion miles. And even at that incomprehensible velocity, it still takes light 4 years and 3 months to reach the nearest star beyond our Sun, about 25 trillion miles away. The closest stellar address there is, and everything beyond it, is farther. Much farther. That is the first honest thing to say about interstellar travel. The distances are so extreme that normal intuition about travel, about getting somewhere by simply going fast enough, breaks down almost immediately. The star, at the other end of that 25 trillion mile gap, is called Proxima Centauri. It is a red dwarf, a category of star that dominates our galaxy by number. But that looks nothing like our Sun. Red dwarfs are small, cool, dim, and extraordinarily long-lived. Proxima Centauri has a mass of roughly 12% of the Sun's. Its diameter is about 14% of the Sun's. It outputs approximately 0.1% of the light our Sun produces. If you replace the Sun with Proxima Centauri, Earth would freeze within days. Everything that lives here would end. The planet would not be meaningfully warmed by anything Proxima provides at Earth's current orbital distance. Red dwarfs are not, in general, the kind of star you'd choose if you were designing a solar system for habitability. But Proxima Centauri is our nearest neighbor, and that proximity gives it an importance that its dim nature would otherwise deny it. Proxima is part of a larger stellar system, a triple-star arrangement called Alpha Centauri, named after the constellation it appears to belong to as seen from Earth. The other two members are dramatically different from Proxima. Alpha Centauri A is a Sun-like star, slightly larger than our Sun, about 10% more massive, and roughly 1.5 times more luminous. If you stood on a planet orbiting Alpha Centauri A and looked at its Sun, you would see something comfortably familiar. Similar color, similar size, similar energy output. Life as we know it could plausibly exist around it, given the right planet at the right distance. Alpha Centauri B is also a relatively normal star, about 90% the mass of the Sun, about half its luminosity. Smaller, dimmer, but still a perfectly mainstream main-sequence star, fusing hydrogen in its core and radiating light in a steady, predictable way. Alpha Centauri A and B orbit each other in an elliptical path. At their closest approach, they're about 11 astronomical units, apart roughly the distance from our Sun to Saturn. At their widest separation, they reach approximately 36 astronomical units. For comparison, Neptune orbits at about 30 astronomical units from our Sun. So, at maximum separation, A and B are farther apart than Neptune is from us. Their orbital period is just under 80 years. They have completed one full orbit since the final years of the Second World War. They will complete their next orbit around the year 2037. Proxima Centauri orbits both of them at a vast remove. Its distance from the AB pair is approximately 13,000 astronomical units, about 0.2 light-years. At that distance, completing one orbit takes roughly 550,000 years. Proxima has been gravitationally bound to this system for billions of years. In all that time, it has completed only a few thousand orbits around the central pair. Stars operate on timescales that make the longest stretches of human history vanish into rounding errors. Now, among these three stars, it is Proxima that sits closest to us. 4.24 light-years to Proxima, 4.37 light-years to Alpha Centauri A and B. The difference in distance is small enough to be negligible from the perspective of any propulsion system we can currently build. What matters is that all three are in the same general direction, at roughly the same extreme distance. They are the next-door neighbors, the immediate beyond. In 2016, astronomers confirmed the existence of a planet orbiting Proxima Centauri, named Proxima Centauri b. The planet is roughly Earth-sized, about 1.3 times Earth's mass, and it orbits within the habitable zone, the range of distances from a star where surface temperatures could allow liquid water to exist. The discovery changed the conversation about Proxima significantly. It transformed our nearest stellar neighbor from merely an interesting astronomical object into a potential destination in the fullest sense, a star that might have a world. Whether Proxima b is actually habitable is a separate and genuinely uncertain question. Proxima Centauri is prone to flares, sudden, powerful eruptions of radiation and charged particles that can be hundreds of times more intense than the worst flares our Sun produces. A planet, orbiting as close as Proxima b, does only about 4.7 million miles from its star. Completing one orbit every 11.5 days would be regularly bombarded by this radiation. Without a strong planetary magnetic field to deflect it, the surface could be periodically sterilized. The planet is also almost certainly tidally locked, one face permanently turned toward the star, one face permanently in darkness, with a narrow zone at the boundary between them, where temperatures might be moderate enough for liquid water. We have not been able to measure Proxima b's atmosphere, magnetic field, or surface composition directly. We detected the planet by observing the tiny wobble it induces in Proxima's motion as it orbits, a technique that reveals mass and orbital period, but little else. What we know is that the planet exists, that it's in the right range of distances for potential habitability, and that it's at the end of a 25 trillion-mile journey. The next nearest star to us is Barnard's star, 6 light-years away, roughly 35 trillion miles. Barnard's star is also a red dwarf, smaller and dimmer even than Proxima Centauri, with a mass of about 14% of the Sun's. It is essentially invisible to the naked eye. What makes Barnard's star notable to astronomers is its proper motion, the rate at which it moves across the sky, as seen from Earth. It moves faster across our line of sight than any other star. Not because it is actually moving faster through space than other stars in any absolute sense, but because it happens to be close enough and angled in a way that makes its lateral motion measurable from year to year, over the span of a human lifetime, Barnard's star noticeably shifts its position relative to the background stars. In about 10,000 years, this motion will carry it close enough to our solar system that it will briefly become our nearest stellar neighbor, surpassing Proxima Centauri in proximity before gradually moving away again. The universe is not static. Our stellar neighborhood is in constant, slow rearrangement. Whether Barnard's star has planets of interest is a question that has been investigated with some urgency, given how close it is. Observations have suggested the possible presence of at least one planet, though confirmation remains elusive. As a potential destination for an early interstellar mission, Barnard's star is a realistic candidate close enough to be somewhat more reachable than the systems beyond it, even if it lacks the cultural resonance of the Alpha Centauri system. After Barnard's star, the list of nearby stellar addresses continues in a relatively gradual staircase of increasing distance. Wolf 359 sits at 7.9 light-years, roughly 46 trillion miles. Another red dwarf, unremarkable in most respects, but a genuine member of our stellar neighborhood. Then, Lalande 21,185 at 8.3 light-years. And then, Sirius. Sirius is the brightest star in the entire night sky, as seen from Earth, not because it is intrinsically the most luminous, but because it combines reasonable brightness with relative closeness. It sits at 8.6 light-years from us, roughly 50 trillion miles. Sirius is a binary system. The primary star, Sirius A, is about twice the mass of the Sun and roughly 25 times more luminous. It is a hot, blue-white star, hotter than our Sun, burning through its hydrogen fuel more rapidly and emitting correspondingly more ultraviolet radiation. Its companion, Sirius B, is a white dwarf. A white dwarf is the exposed core of a star that has completed its main sequence life, exhausted its hydrogen fuel, expanded into a red giant, shed its outer layers, and left behind a dense, Earth-sized remnant that slowly cools over billions of years. Sirius B was once a star considerably more massive than our Sun. It has long since completed that life. The system as a whole is scientifically interesting, but as a destination for habitable worlds, Sirius A's intense radiation makes prospects dim. It is doubtful that planets in Sirius A's habitable zone could maintain conditions favorable to life as we know it under that level of ultraviolet bombardment. Sirius represents a compelling astronomical target, but probably not a colonization destination. These are the neighbors. Proxima Centauri at 4.2, 4 light-years. Barnard's star at 6. Wolf 359 at 7.9. Lalande 21,185 at 8.3. Sirius at 8.6. All within 9 light-years. All accessible, in principle, to any technology capable of crossing interstellar distances at all. None accessible to anything we have actually built. And then there is TRAPPIST-1. It's located approximately 40 light-years from Earth, about 235 trillion miles. That is 10 times farther than Proxima Centauri. Under any propulsion concept we can currently build or realistically envision building in the near term, TRAPPIST-1 represents a journey 10 times longer than the already brutal voyage to the nearest star. The reason TRAPPIST-1 appears in every serious discussion of interstellar destinations is not its proximity. It is what the science tells us is there. In 2017, astronomers announced the confirmed discovery of at least 7 Earth-sized planets orbiting TRAPPIST-1. 7 Earth-sized worlds around a single star. 3 of those planets orbit simultaneously within the star's habitable zone. That number 3, potentially habitable worlds in one system, has no parallel anywhere else in the known universe. Our own solar system, for comparison, has 1 world in the habitable zone with confirmed life, and perhaps 1 or 2 more at the edges of that zone that might have supported it at some point in the past. TRAPPIST-1 has 3 candidates at once. The star itself is what astronomers call an ultra-cool red dwarf, smaller, cooler, and dimmer than even Proxima Centauri. Its mass is roughly 8% of the Sun's. Its luminosity is about 0.3% of the Sun's. Because it is so dim, the habitable zone around it sits very close, much closer than the habitable zone around our Sun. To receive enough warmth for liquid water, a planet around TRAPPIST-1 must orbit extremely close to its star. All 7 known planets do exactly that. The innermost planet completes 1 orbit in about 1.5 Earth days. The outermost known planet takes roughly 19 Earth days. This closeness brings familiar complications. Tidal locking is almost certain for all or most of the planets, one face perpetually toward the star, the other in perpetual night. TRAPPIST-1 also produces flares, as red dwarfs commonly do, potentially threatening the atmospheric integrity of its closely orbiting worlds. Whether any of the 3 habitable zone planets designated TRAPPIST-1, E, F, and G actually host liquid water or life is completely unknown. We have detected them through the transit method, watching the slight dimming of TRAPPIST-1's light as each planet passes in front of it. That tells us their sizes and orbital periods. More recent observations have begun to constrain their atmospheric compositions, with some planets showing signs that are either consistent with or not inconsistent with habitable conditions. But we are looking from 40 light-years away, through instruments that, for all their sophistication, are at the limits of what physics allows for studying worlds at these distances. What we know about TRAPPIST-1 is enough to make it, arguably, the most scientifically important stellar system in the known sky. After our own, what we don't know about it could fill every scientific journal ever published. And getting there to find out is not a problem of ambition. It is a problem of physics, engineering, and time. So, let's look at where we actually are. Because the distance between our current capability and what interstellar travel requires is not a gap to be casually noted and moved past. It is the central fact of the entire problem. Voyager 1 is our most distant spacecraft. It launched from Cape Canaveral on September 5, 1977. It has been traveling continuously since then for nearly 50 years. In August 2012, after 35 years of travel, it crossed the heliopause, the outer boundary of the Sun's magnetic and particle influence, where the solar wind gives way to the interstellar medium. Voyager 1 became the first human-made object to enter true interstellar space. That is a genuine milestone. It is also a deeply sobering one when you look at the numbers. Voyager 1 currently travels at approximately 38,000 miles per hour relative to the Sun. That speed is essentially incomprehensible by everyday human standards. A commercial airliner flies at around 600 miles per hour. The fastest jet aircraft ever built, the Lockheed SR-71 Blackbird, topped out at about 2,200 miles per hour. A rifle bullet travels at roughly 2,000 miles per hour. Voyager 1 moves at nearly 20 times the speed of a rifle bullet. Continuously. It has covered approximately 14 billion miles from Earth, which sounds enormous, until you compare it to the distance to Proxima Centauri. 25 trillion miles. Voyager 1, after 50 years of constant travel, has covered roughly 1/1000th of the distance to our nearest stellar neighbor. At its current speed, Voyager 1 would arrive at Proxima Centauri in approximately 77,000 years. Not 73. 73,000. To Barnard's star at 6 light years, about 103,000 years. To Wolf 359 at 7.9, roughly 136,000 years. To Sirius at 8.6 light years, approximately 148,000 years. To TRAPPIST-1 at 40 light years, around 680,000 years. The Parker Solar Probe, which achieves greater velocities than Voyager by using Venus gravity, assists to swing repeatedly close to the Sun, reached a peak speed of around 430,000 miles per hour in December 2024, roughly 10 times Voyager 1. At that speed, pointed toward Proxima Centauri, the trip takes about 6,800 years. 7,000 years ago, the earliest writing systems were just emerging in Mesopotamia. No organized state had yet appeared in what would become Greece. The pyramids at Giza would not be built for another 1,000 years. The entire span from that moment to now, every war, every civilization, every scientific discovery, every piece of art, every generation of human beings who lived and built and struggled and created is shorter than what our fastest spacecraft would need to reach the nearest star. This is not a crisis. It is simply the truth. And every proposal for interstellar travel has to begin by acknowledging it. You cannot optimize your way from 77,000 years to 40. You cannot tweak your way to the stars. You need a fundamentally different approach to propulsion. The question is what that approach looks like and whether we can actually build it. Let's begin with the physics that governs the problem. Because understanding why current rockets fail is essential to understanding why the proposed solutions are so demanding. Every rocket ever built, regardless of fuel, type, or design, works on the same principle. You throw mass out the back. The reaction from throwing that mass pushes you forward. This is Newton's third law applied to propulsion. The key variable is exhaust velocity, how fast the mass exits the engine. The faster the exhaust, the more efficient the rocket. More push from less propellant. The Russian scientist Konstantin Tsiolkovsky derived the equation that describes this relationship in the late 19th century. It is called the Tsiolkovsky rocket equation, and it is the central constraint governing all rocket propulsion. The equation says that the change in velocity a rocket can achieve equals the exhaust velocity multiplied by the natural logarithm of the ratio of the rocket's initial mass to its final mass. In practical terms, the faster you want to go, the more of your total launch mass must be propellant. And this relationship is logarithmic, which means it gets dramatically worse as the target speed increases. To double your speed, you need to square your fuel-to-payload ratio. To triple your speed, you cube it. The math compounds viciously against you. For chemical rockets, which burn hydrogen and oxygen or similar combinations, exhaust velocities top out at around 10 to 15,000 miles per hour. That sounds fast. At those exhaust velocities, reaching even 1% of the speed of light, about 1,860,000 miles per hour, would require a vehicle where the propellant makes up an essentially impossible fraction of the total mass. The ratio becomes larger than any physically constructible rocket. The fuel would outweigh the spacecraft by factors that exceed any material's structural capability. This is not a failure of engineering. This is what the physics says. Chemical combustion simply does not release enough energy per kilogram of fuel to get a spacecraft to interstellar speeds. The energy density is too low by many orders of magnitude. The gap between chemical rockets and interstellar travel is not a gap that better design closes. It is a gap that requires a different category of energy source. Nuclear energy contains that energy source. Atomic reactions, whether fission or fusion, release energy through fundamentally different mechanisms than chemical combustion. And the difference in energy density is enormous. A kilogram of nuclear fuel releases roughly millions of times more energy than a kilogram of chemical fuel. That difference is what makes the math begin to work. But nuclear propulsion covers a wide range of technologies, and they are not equally capable. The most conservative nuclear propulsion concept is the nuclear thermal rocket. The idea is straightforward. Instead of burning chemical fuel to heat a propellant, you use a nuclear fission reactor to heat it instead. The propellant, usually liquid hydrogen, flows through the reactor core, absorbs heat, and exits through a nozzle at very high temperature, producing thrust. The advantage over chemical rockets is exhaust velocity. A nuclear thermal rocket can achieve exhaust velocities roughly 2 to 3 times those of the best chemical engines. NASA actually built and tested nuclear thermal rocket engines in the 1960s under a program called NERVA, Nuclear Engine for Rocket Vehicle Application. Multiple engine designs were tested at full power. They worked. They were more efficient than any chemical rocket ever built. They were cancelled for political and budgetary reasons, not because the technology failed. In recent years, both NASA and the US Department of Defense have reinvested in nuclear thermal propulsion research, with the goal of enabling faster crewed missions to Mars and potentially missions to the outer solar system. For the purposes of interstellar travel, however, nuclear thermal propulsion is insufficient. 2 to 3 times the exhaust velocity of chemical rockets moves the needle on the Tsiolkovsky equation, but not nearly far enough. You've gone from completely impossible to still completely impossible. Nuclear thermal propulsion is a meaningful upgrade for solar system exploration. For crossing 25 trillion miles in any relevant time frame, it does nothing useful. It remains in the wrong category of solution. The first concept that genuinely begins to change the equation for interstellar travel is nuclear pulse propulsion. The basic idea is famous for being simultaneously elegant and completely insane. You detonate nuclear bombs behind the spacecraft. Each explosion produces a powerful blast of plasma and radiation. A massive, extremely strong plate at the rear of the ship. The pusher plate absorbs this blast. Shock absorbers between the pusher plate and the body of the spacecraft translate the violent impulse into a sustained forward push. You repeat this process, continuously detonating bombs at regular intervals, absorbing each blast, accumulating velocity. This concept was developed in serious technical detail in the late 1950s and early 1960s under a program called Project Orion, run by the General Atomics Company, with support from the US Air Force and later NASA. The physicists involved were not fringe thinkers. Freeman Dyson, one of the most respected theoretical physicists of the 20th century, was a central contributor. He believed, and stated publicly on multiple occasions, that nuclear pulse propulsion was the most practical approach to large-scale interstellar travel that had been seriously studied. The analysis suggested that a ship powered by nuclear pulse propulsion could, depending on bomb yield and detonation frequency, reach speeds between 3 and 10% of the speed of light. At 3% of light speed, the journey to Proxima Centauri takes about 140 years. At 10%, about 42 years. These are generational timescales for the closer destinations, but they are at least finite, in a way that 77,000 years is not. More significantly, the ships being discussed were not tiny probes. Project Orion concepts involve vehicles the size of city blocks, vessels massive enough to carry not just crew, but substantial infrastructure, equipment, and supplies for the voyage, and for whatever they found at the destination. At that scale, a nuclear pulse ship could carry everything needed for a genuine interstellar mission, not just a flyby. The engineering challenges were enormous, but not obviously impossible. The pusher plate would need to be extraordinarily robust, capable of withstanding thousands of nuclear explosions without structural failure. The shock absorber system would need to operate reliably through each of those detonations, converting each violent impulse into smooth forward momentum. The nuclear devices themselves, potentially thousands of them, would need to be stored safely and detonated reliably throughout the journey. None of these engineering challenges were solved before Project Orion ended, but none were shown to be unsolvable. The program was terminated not because the physics was wrong, and not because the engineering proved impossible. It was terminated primarily because of the Partial Nuclear Test Ban Treaty of 1963, which prohibited nuclear detonations in space and in the atmosphere. Building a nuclear pulse ship and launching it even for a civilian scientific mission would require detonating thousands of nuclear devices in space. Politically, in 1963, and in the decades since, that has been impossible. Whether a future civilization could reach the political consensus required to permit it is a different question. The treaty is an agreement between nations. Agreements can be changed. What the physics says is, it would work. What politics says is, not yet. The step beyond nuclear pulse propulsion, in terms of both capability and technical difficulty, is fusion propulsion. The difference between fission and fusion is fundamental. Fission splits heavy atomic nuclei, uranium or plutonium, and releases energy from that splitting. Fusion combines light nuclei forms of hydrogen and releases energy from that combination. The sun runs on fusion. So do hydrogen bombs. The fraction of mass converted to energy in a fusion reaction is significantly larger than in a fission reaction, and the energy released per unit mass of fuel is correspondingly greater. For propulsion, what matters is the exhaust velocity achievable. In a fusion rocket, the reaction products, typically helium nuclei and other particles, exit the engine at velocities that could reach between 5 and 15% of the speed of light, depending on the specific fusion reaction used and the efficiency of the engine. At those exhaust velocities, the Tsiolkovsky equation produces much more tractable results. A fusion-propelled spacecraft could reach 10 to 20% of light speed while carrying a fuel mass that, while large, remains within the bounds of what you could plausibly build and launch. At 10% of light speed, Proxima Centauri is 42 years away. At 20%, it's 21 years. Barnard's star, at 10% of light speed, 60 years. Sirius, at 10%, 86 years. These are demanding journeys. 40 years is a significant portion of a human career. 86 years is a multi-generational commitment. But they are journeys that a civilization with fusion propulsion could actually undertake with real human crews, real scientific missions, real destinations. The problem is that we do not have fusion propulsion. We do not yet have sustained, controlled fusion at all. After more than 70 years of effort, beginning in earnest in the 1950s, with programs in the United States, the Soviet Union, and Britain achieving a controlled fusion reaction that produces more energy than it consumes, has proven extraordinarily difficult. The temperatures required for fusion, tens of millions of degrees, conditions under which no material container can survive direct contact with the plasma, demand creative solutions for confinement. The two main approaches are magnetic confinement, using powerful electromagnetic fields to hold the superheated plasma away from solid surfaces, and inertial confinement, using powerful lasers or other drivers to compress a fuel target so rapidly that fusion occurs before the material can escape. In December 2022, the National Ignition Facility in California achieved what physicists call ignition, a fusion reaction that produced more energy than the laser energy delivered to the fuel pellet. 192 laser beams delivering more than 2 million joules of ultraviolet energy. About 3.15 megajoules of fusion energy released. More out than in. A genuine milestone. But more out than in a laboratory setting where the enormous energy cost of running the laser itself is set aside, is a very different thing from a power plant that produces commercially useful energy. And a power plant is a very different thing from a compact engine that sustains fusion continuously for decades in the vacuum of space. The path from where we are to fusion propulsion for interstellar travel is long. It is probably measured in decades, maybe the better part of a century. But unlike antimatter propulsion, which will come to fusion, has a visible developmental pathway. The physics is understood. The engineering challenges, while severe, are not obviously insolvable. If fusion energy becomes practical on Earth, the technology base for compact fusion rockets follows as a natural development, driven by exactly the same pressures of miniaturization and reliability that have driven every other propulsion technology from laboratory to operational. Fusion propulsion is the first serious candidate for getting human beings to the nearest stars within a human lifetime. It doesn't exist yet. But it isn't fantasy. Antimatter propulsion occupies the far end of the theoretical spectrum. It is also the most perfect solution imaginable and the most impractical one currently known. When a particle of ordinary matter encounters its antimatter equivalent, both annihilate completely. Every last bit of mass converts directly to energy. The process is described by Einstein's equation, E equals mc squared, where c is the speed of light, 186,000 miles per second. The c² term is an enormous number. Even a small amount of mass, fully converted to energy, produces a staggering result. The efficiency of antimatter annihilation is 100%, not 99%, not 95%. 100% of the mass converted completely to energy. No other reaction in physics comes close. Nuclear fission converts less than 1% of mass to energy. Fusion converts roughly 1%. Chemical combustion converts a fraction of a percent so small it barely registers. Antimatter annihilation converts everything. In propulsion terms, a perfectly efficient antimatter engine could achieve exhaust velocities approaching the speed of light itself. The theoretical performance ceiling is the highest any rocket could ever reach within known physics. An antimatter-propelled spacecraft could, in principle, accelerate to a large fraction of the speed of light, with a fuel mass that is reasonable relative to the spacecraft's total mass. The journey to Proxima Centauri could be measured in years rather than decades. The journey to TRAPPIST, one could be completed within a human lifetime, with time to spare. The problem is that we cannot make antimatter in useful quantities, and probably cannot do so with any technology we can currently envision. Antimatter exists in nature. It is produced briefly in high-energy cosmic ray collisions and in the decay of certain radioactive isotopes. It can be produced deliberately in particle accelerators. But the amounts are microscopic. Particle accelerators around the world, facilities consuming enormous amounts of electrical power and operating continuously produce antiprotons in quantities measured in nanograms per year. A nanogram is 1/1000th of a gram. A paperclip weighs about a gram. That energy from 1 gram would not be enough to propel any meaningful spacecraft to interstellar speeds. For a crewed mission at a significant fraction of light speed, you would need kilograms of antimatter, possibly metric tons. The gap between nanograms per year of current production and metric tons of operational fuel is not an engineering challenge. It is a difference so extreme that no incremental improvement in current technology begins to bridge it. Storing antimatter presents an equally severe challenge. Antimatter cannot touch ordinary matter. If it does, both annihilate immediately. You cannot put antimatter in a container because the container is made of ordinary matter and would be destroyed on contact. Instead, you have to suspend the antimatter in electromagnetic fields, magnetic traps that keep the antiparticles hovering in empty space, never touching any solid surface. The technology to do this exists in small-scale laboratory settings. Maintaining it for decades in the hostile radiation environment of interstellar space, with no possibility of maintenance or repair, if something goes wrong, is a challenge for which no engineering solution currently exists. A single failure in the containment system at any point during a 40-year voyage releases the antimatter fuel. The result is an explosion equivalent to multiple nuclear warheads. There is no backup. There is no safe mode. Antimatter propulsion remains the most elegant theoretical solution to interstellar travel. For the foreseeable future, it is also effectively unreachable. We mention it not to dismiss it, but because understanding what perfect looks like is useful when you're evaluating what actually possible looks like. Laser lightsails represent a completely different philosophy from every propulsion concept we've discussed. Rather than accelerating by carrying your energy source with you, you leave the energy source behind. You build a massive laser installation in orbit or on the ground and fire it at a spacecraft equipped with an ultra-thin, highly reflective sail. Light carries momentum. This is not metaphorical. Photons exert a measurable pressure when they strike a surface. It is tiny, absurdly small, for any everyday surface. But at sufficient laser power, applied to a sufficiently lightweight sail, photons can push a spacecraft to very high speeds. The key is that the spacecraft doesn't need to carry fuel at all. The energy comes from the laser, which stays behind. The spacecraft is almost pure payload and sail. The Breakthrough Starshot initiative, announced in 2016 and backed by Yuri Milner, along with a range of prominent scientists, proposed exactly this approach. The concept envisions building a laser array with a combined output of roughly 100 gigawatts, comparable to the combined output of 100 large nuclear power plants. This array would be aimed at tiny, gram-scale probes equipped with sails a few meters across. The laser would fire for a matter of minutes. In that time, the probe would be accelerated to approximately 20% of the speed of light. At that velocity, the journey to Proxima Centauri takes about 21 years. 21 years. That is not a typo. That is what laser propulsion at 20% of light speed delivers to the nearest star. It is a genuinely revolutionary result compared to the 77,000 years Voyager 1 would require. The engineering challenges of Breakthrough Starshot are significant and real, but they are at least in the domain of engineering rather than new physics. The laser array requires precision optical systems capable of keeping a beam focused on a sail the size of a small table that is already moving away at tens of thousands of miles per second. The probes themselves, to fit within the gram-scale mass budget, must pack all their scientific instruments and communication systems into essentially microscopic form factors. The transmitter, capable of sending data back 4 light-years to Earth, would need to operate at extremely low power, requiring enormous receiving dishes on Earth to detect the signal. Data transmission rates would be low. Getting back even a handful of high-resolution images from the Proxima Centauri system might take months or years of continuous transmission after the flyby. But the most fundamental limitation of laser light sails is that they cannot stop. The laser array is back at Earth. It pushed the probe forward. Nothing at Proxima Centauri is pushing backward to slow it down. The probe arrives at 20% of the speed of light and flies through the system in a matter of hours. Whatever it can observe and transmit during those hours is the entirety of its scientific return. Then it disappears into deep space on the far side of the Alpha Centauri system, continuing outward at the same speed indefinitely. For a gram-scale robotic probe with a camera and spectrometer, a flyby might be acceptable. The scientific return, the first close-up images and measurements of another star system taken from within that system, would be extraordinary by any measure. But for a crewed vessel, for a mission intended to enter orbit and study a star system in detail, for anything resembling colonization or sustained exploration, a flyby is not sufficient. You need to stop when you arrive. And laser light sails, as currently conceived, provide no mechanism for stopping. There have been proposals for using a separate, smaller sail deployed at the destination to slow down using the star's own light pressure. The physics is sound. The engineering challenge is immense. Red dwarf stars, like Proxima Centauri, produce relatively little light, which means the decelerating force from stellar photon pressure is small, slowing from 20% of light speed to orbital velocity around Proxima. Using only the star's light pressure alone would take decades of deceleration, possibly longer than the outbound journey took. The mission profile becomes extraordinarily long and complex. Laser lightsails are, at this moment, the most credible near-term candidate for getting anything, any sensor package, any scientific instrument to another star system in less than a century. For that narrowly defined purpose, they may be achievable with technology that could be developed within decades. For getting people to another star system in any meaningful way, they are not the answer. Generation ships occupy a unique position in the catalogue of possible approaches. They are not a faster solution. They do not solve the propulsion problem. They are a different answer to a different version of the question. If you cannot cross the distance in a single human lifetime, and for most realistic near-term propulsion scenarios, you cannot. Then you build a ship that carries multiple lifetimes. The people who launch the mission are not the people who complete it. Their children travel for much of the journey. Their grandchildren and their grandchildren's grandchildren and generations beyond them are the ones who arrive at another sun. The generation ship concept has been part of serious scientific and philosophical discussion for decades. At nuclear pulse propulsion speeds of 3 to 5% of light speed, the trip to Proxima Centauri takes between 85 and 140 years. 2 to 3 human generations. At more modest speeds, say, 1% of light speed, which might be achievable with near-future nuclear propulsion of various kinds, the journey takes over 400 years. More than 10 generations. For Barnard's star, at 1% of light speed, about 600 years. For Sirius, roughly 860 years. For TRAPPIST, 1 at 1% of light speed, 4,000 years. At 5% of light speed nuclear pulse territory at the upper end TRAPPIST, 1 is 800 years away. 20 to 30 generations. A generation ship is not primarily a spacecraft. It is a civilization in transit. A closed, self-contained society that must sustain itself in complete isolation across decades or centuries, with no resupply from outside, no real-time communication with Earth beyond radio signals that take years to travel in each direction, and no external support of any kind for any problem that arises. The physical requirements for such a vessel are extraordinary. Food production must be entirely self-contained, hydroponic and aeroponic growing systems that recycle nutrients continuously and produce enough calories for the entire population without any input from outside. Water recycling must be essentially perfect. Not 99% efficient. Effectively, 100%. Every drop of water must be reclaimed and purified and returned to use indefinitely for generations. Air composition must be maintained, precisely oxygen produced by plants or electrochemical systems, carbon dioxide scrubbed out, trace contaminants removed in a fully closed ecosystem. Medical capability must encompass everything. Every illness, every injury, every surgical procedure, every mental health crisis, every complication of pregnancy, every age-related disease. Across the full lifespan of every person born aboard, with no ability to transfer a patient to a specialist facility or import a treatment not available on the ship. Manufacturing capability must be sufficient to fabricate replacement parts for any system aboard the vessel. Not some systems, any system. Because systems fail. Every component that operates continuously for decades will eventually degrade or break. The generation ship must be able to repair and replace anything on board, using raw materials carried on board, using knowledge and skills that can be transferred from one generation to the next. If the water recycling system develops a fault 300 years into the voyage and no one alive on the ship knows how to fix it, the mission ends for everyone. That is the engineering baseline. And it is not the hardest part of the problem. The hardest part of the problem is the people. Consider what it means to be born aboard a generation ship. You emerge into a world of metal walls and artificial light. The sky above you is a ceiling. The ground beneath you curves upward in the distance if the ship uses centrifugal force for gravity. You grow up in corridors and hydroponics bays, and common rooms and dormitories. You learn about Earth from recordings and stories and the descriptions of elders. Forests, oceans, rain, open sky. You know what these things are. You have never experienced any of them. You never will. Your entire social universe is the ship's population. The same faces, the same voices, the same conflicts and relationships and hierarchies for your entire life. You are assigned work, likely work determined by the ship's needs rather than your personal preferences, because the mission requires people to fill specific roles and it cannot afford to have gaps in critical expertise. You may have some freedom in your personal choices, but you do not have the choice to leave. You cannot walk out. There is nowhere to go. You are on a vessel traveling through interstellar space with no habitable planet within reach for decades or centuries. Every door that opens in the ship leads to another part of the ship. That is the entirety of your physical freedom. And you are there not because you chose to be there. You are there because your ancestors chose it before you existed. The mission, the destination, the purpose, all of it was decided by people you never knew, about a future you were born into without consent. Studies of isolated human communities consistently show that long-term confinement increases depression, increases interpersonal conflict, degrades social trust, and strains governance systems that were adequate under normal conditions. Research stations in Antarctica, submarine crews, long-duration International Space Station missions. All of these provide data on how human beings respond to closed, isolated environments over periods of months to a couple of years. The findings are consistent. Humans struggle, even knowing the confinement is temporary, even knowing the exit is coming. Now, remove the temporariness. Now make the isolation not months, but the entire span of a human life. Now remove the option of leaving, not just practically, but literally. The generation ship problem is not primarily an engineering problem. It is a civilization design problem. You have to build social structures, governance, culture, education, conflict, resolution, justice, meaning, identity that can sustain a community across generations in a context no human civilization has ever experienced. You have to ensure that knowledge transfers perfectly from one generation to the next. Not approximately, perfectly. Because losing critical knowledge is not a recoverable mistake when you are a self-contained world in the void between stars. You have to ensure that the mission's purpose survives cultural drift across centuries. The people of the third generation may not feel the same connection to the mission's rationale as the people who launched. The people of the 10th generation may feel none at all. If the mission is to reach a specific star and settle a specific world, you need that goal to remain alive and operative in the culture of the ship across all the generations in between. Human institutions have maintained purposes across centuries before religions, monarchies, academic traditions. But none of them faced the specific constraint of complete physical isolation with no external reinforcement. And none of them had consequences for institutional failure as immediate and absolute as a spacecraft in which everyone ends. A generation ship is not impossible. Nothing about it violates physical law. But it represents a challenge in social engineering for which we have no proven solution. Building one would be an act of extraordinary faith in our ability to solve problems we have never faced. The cryosleep alternative is worth serious consideration precisely because it converts the hardest part of the generation ship problem, the human social problem, back into an engineering problem. The idea is to freeze the crew for the duration of the voyage. They stop aging. They stop consuming food and water and oxygen. They do not need meaning or governance or cultural continuity. They are not experiencing the passage of time. They launch, and they wake up at the destination, subjectively, as though no time has passed. A ship with a crew in cryosleep does not need the complex social infrastructure of a generation ship. It needs a robust automated system for maintaining the frozen passengers safely, monitoring their status, and keeping the ship operational for the full duration of the voyage. Perhaps a small skeleton crew remains awake, rotating in shifts to handle maintenance and emergencies, while the majority of passengers sleep through the journey. The social problem shrinks from civilization scale to small team scale. The engineering problem that replaces it is not trivial, but it is tractable in a way that centuries of social dynamics are not. The biological reality is that we cannot currently do this with human beings. We can preserve cells and simple tissues through cryopreservation, suspending biological water with protective chemicals before freezing to prevent the ice crystal formation that would otherwise rupture cell membranes and destroy cellular architecture. We have preserved embryos and some organs. We are making progress on more complex biological systems in animal models. But freezing an intact adult human being with trillions of cells of dozens of different types, organized into structures of extraordinary complexity, including the brain and all its neural connections, and reviving that person later with full function and no neurological damage, is a problem of a different order entirely. No human being has ever survived this. No animal larger than a small insect has been demonstrated to survive it with full viability. The research continues. Some of it is genuinely promising at the level of individual organs and tissues. The specific challenge of whole-body cryopreservation and revival of large mammals remains open. Whether it will be solved is a genuinely uncertain question. If it is, cryosleep transforms the generation ship problem. It makes it manageable. It allows a relatively small crew to board, sleep through decades or centuries, and wake up at the destination as essentially the same people who launched. If it is not solved, if the biology proves intractable, then generation ships, in the full social sense, may be the only option for crewed interstellar travel on timescales longer than a single human lifetime. Now, here is where the physics introduces something that most discussions of interstellar travel mention briefly and then move past, even though it changes every timeline calculation fundamentally. Time dilation. Einstein's special theory of relativity, published in 1905, contains a prediction so counterintuitive that it sounds like science fiction the first time you hear it. And yet, it has been confirmed by experiment repeatedly in multiple different settings, with measurements that leave no reasonable doubt. The prediction is this: time does not pass at the same rate for all observers. The faster you move relative to another observer, the more slowly time passes for you from that observer's perspective. This is not a metaphor. It is not an approximation. It is not a philosophical statement about perception. It is a precise, measurable, quantitative physical phenomenon described by equations that produce numbers, and those numbers match experimental measurements to high accuracy. The effect is described by what physicists call the Lorentz factor, usually written with the Greek letter gamma. At everyday speeds, anything we encounter in ordinary life, the Lorentz factor is essentially 1. The difference in time passage is unmeasurably small. But as speed approaches the speed of light, the factor grows. At 90% of light speed, the Lorentz factor is about 2.3. Time on the moving ship runs at roughly 44% of the rate of time experienced by stationary observers. For every year felt by the crew, about 2 years and 3 months pass on Earth. At 99% of light speed, the factor reaches roughly 7. 1 year of crew experience corresponds to 7 years of Earth time. At 99.9% of light speed, the factor exceeds 22. 1 year aboard corresponds to more than 22 years on Earth. These numbers are not thought experiments. Muons, subatomic particles, created by cosmic ray collisions in Earth's upper atmosphere, travel downward at nearly the speed of light. They decay so rapidly that, based on the distance they travel, they should be gone long before reaching the ground. They are not gone. They reach the ground. Because from Earth's perspective, their internal clock runs so slowly at near light speeds that they live long enough to complete the journey. Atomic clocks placed on aircraft tick at a measurably different rate than identical clocks on the ground. GPS satellites carry clocks that must be corrected for relativistic time differences to maintain the accuracy the system requires for navigation. Time dilation is not theoretical. It is operational. What does this mean for interstellar travel? At 10% of light speed, the kind of speed a mature fusion drive might achieve, the Lorentz factor, is about 1.005. The effect is almost negligible. A 42-year journey to Proxima Centauri would see the crew arrive about 5 months younger than if they'd stayed on Earth. Not a meaningful difference. At 50% of light speed, the factor is about 1.15. Time on the ship runs at about 87% the rate of Earth time. During an approximately 8.5-year voyage to Proxima Centauri, the crew would experience about 7.4 years, while roughly 8.5 pass on Earth. More noticeable, but still not the dominant feature of the journey. At 90% of light speed, which would require propulsion technology well beyond anything currently demonstrated, the factor becomes approximately 2.3. The approximately 4.7-year voyage to Proxima Centauri, as measured by Earth observers, would feel like about 2 years to the crew. This is where the effect starts to matter practically. Now, apply these numbers to TRAPPIST-1. TRAPPIST-1 is 40 light-years away. At 90% of light speed, the journey takes about 44 years as measured by Earth observers. The crew would experience about 19 years. At 99% of light speed, The journey takes about 40 years from Earth's perspective, but the crew experiences less than 6 years. 6 subjective years to travel 40 light years. That is the mathematics of time dilation, applied to the most ambitious, realistic interstellar destination. For a crew member who boarded the ship at age 30, this means arriving at TRAPPIST-1 biologically in their mid-30s. Meanwhile, on Earth, 40 years have passed. The world they left behind has changed enormously. People they knew are old. Some of them are gone. Their children, if they had any before departure, are themselves approaching middle age. And this is before the return journey, which would bring another 6 subjective years and another 40 years of Earth time. Board the ship at 30. Arrive at TRAPPIST-1 biologically at 36. Return to Earth, biologically at 42. Earth, 80 years have passed. The time dilation effect sounds like a gift when you first encounter it. You can travel to the stars and barely age. It is a gift with a price that the physics makes unavoidable. You buy subjective travel time with objective disconnection from the world you left. Every person you left behind, every relationship you had, every institution and culture and context that shaped you, all of it has moved on by decades or centuries in the time you were gone. You return to a world that remembers you only dimly, if at all. Your children do not know you. Your grandchildren think of you, if they think of you at all, as a historical figure rather than a person. This is not science fiction. It is the direct consequence of physics, applied to the actual distances of actual nearby stars. Interstellar travel at relativistic speeds is not just a physical journey. It is a permanent departure from the timeline of everyone you leave behind. No propulsion system can change that. It is written into the structure of space-time itself. There is a problem in interstellar travel that doesn't receive the attention it deserves relative to its importance. Deceleration. Every propulsion discussion focuses on acceleration. How do you get to interstellar speeds? But arriving at a star system is not the same as reaching it. Arriving means stopping, entering orbit, positioning yourself to study the planets, potentially landing. To do any of those things, you have to slow down from whatever speed you traveled at. And slowing down requires exactly as much energy as speeding up. With a laser light sail, the situation is straightforward and unfortunate. The laser is behind you. It pushed you toward the destination. There is nothing at the destination to push you backward. You arrive at 20% of the speed of light and continue right through the system. You have hours, perhaps a couple of days, if you plan your flyby trajectory carefully, to observe and transmit data. Then, you're on the far side, receding from the system at 20% of light speed, unable to return. For a nuclear pulse or fusion drive spacecraft, deceleration is possible in principle. You flip the spacecraft and fire your engine against your direction of travel. But this requires exactly as much fuel as the initial acceleration. Your propellant load effectively doubles. You burn the first half, accelerating. You burn the second half, decelerating. The Tsiolkovsky equation is merciless on this point. Every kilogram of fuel you need for deceleration is a kilogram you had to accelerate during the outbound journey, which required fuel, which required more fuel. The mass ratios compound in a deeply inconvenient direction. Several proposals have been made for using the destination environment to brake rather than carrying deceleration fuel. The magsail concept involves deploying a large loop of superconducting wire at the spacecraft's bow as you approach the target system. This loop generates a magnetic field. The stellar wind charged particles continuously streaming outward from the star interacts with this field, creating drag. You slow down without burning any propellant. The concept is elegant and the physics is real. The practical limitations depend heavily on the specific star. Red dwarf stars, including Proxima Centauri and TRAPPIST-1, have relatively weak stellar winds compared to Sun-like stars. Less charged particle flux means less braking force. A magsail, decelerating against Proxima's stellar wind from 5% of light speed, would require decades of gradual deceleration before reaching orbital velocity. It extends the total mission duration significantly. Another proposal uses the destination star's own light as a brake. You flip a sail toward the approaching star rather than the laser behind you. The star's photons push you backward, decelerating the spacecraft. For Sun-like stars with substantial light output, this can work. For red dwarfs dim enough that you have to orbit very close just to stay warm, the braking force from photon pressure is limited. Again, deceleration times stretch into decades. The deceleration problem is not physically impossible. It is physically demanding in ways that compound every other challenge in the mission design. For a reconnaissance flyby of Proxima Centauri or a high-speed pass through the TRAPPIST-1 system with no intention of stopping, it is not a problem. For any mission that intends to do real science in orbit or land on a planet or establish any presence in another star system, the deceleration problem is half of the propulsion challenge. Designs that ignore it are designs for unmanned scouts, not for anything that represents humanity actually going somewhere. Now, put all of this together into what a real mission actually looks like for each destination, with honest technology in mind. Proxima Centauri first. 4.24 light-years. The most optimistic, near-term realistic scenario is a breakthrough Starshot-style lightsail probe, gram-scale instrument package. Laser accelerated to 20% of light speed. Journey time, approximately 21 years. No stopping. Data transmitted back arrives at Earth 4 years after the flyby. Total time, from launch to first data received from within another star system, roughly 25 years. That is potentially achievable within the latter half of this century, given sustained investment and progress on the laser array technology. It would produce the most extraordinary scientific result in history. The first close-up measurements of another star system taken from within it. And it would tell us almost nothing that requires human presence to learn. A crewed mission to Proxima Centauri requires a different accounting. With a fusion drive achieving 10% of light speed, the journey takes 42 years, one way. A crew member who departs at 30 arrives at Proxima at age 72. The return journey, if it happens, brings them back at 114 years old by Earth's calendar, or somewhat younger by the ship's clock, due to time dilation at 10% of light speed. No currently living person has reached 114. The mission is a one-way commitment, practically speaking. You go, you do your science, you transmit your findings. You don't come back. Or if you do, you come back to a world 84 years older than the one you left. With nuclear pulse propulsion at 3% of light speed, the journey extends to about 140 years. 2 full generations. The crew that launches is the crew that is gone before arrival. Their children or grandchildren arrive. This is a generation ship, a small one, for a relatively close target, but a generation ship nonetheless. With all of the social and psychological challenges that entails. Barnard's star at 6 light years. At 10% of light speed, 60 years. A single, very long career, from launch to arrival, possible for someone who departs young and arrives in very old age. But without confirmed habitable planets, the motivation to choose Barnard's star over Proxima is limited unless its planetary system turns out to hold something extraordinary. At 3% of light speed, about 200 years, 7 to 8 generations. A genuine multi-generational commitment with no guaranteed payoff. Sirius at 8.6 light years. At 10% of light speed, 86 years. 2 human generations, in the most minimal sense. The mission is multi-generational. The destination, as discussed, is not compelling for colonization. The science is interesting, but not so uniquely compelling that it justifies the mission over the closer options. TRAPPIST, 1 at 40 light years. This is where every timeline gets brutal. At 3% of light speed, over 1,300 years, 40+ generations. An entire medieval epoch, just in transit. The civilization that boards the ship and the civilization that arrives have essentially nothing in common except lineage. At 10% of light speed, 400 years, 13 to 15 generations. The mission spans more time than from Shakespeare's era to the present. At 20% of light-speed fusion propulsion, operating near its theoretical upper limit, 200 years. 7 to 8 generations. At 50% of light-speed technology that does not exist and has no clear development path, 80 years. 2 human generations. At 90% of light speed, purely theoretical, about 44 years from Earth's reference frame, 19 years of crew time. An extraordinary result, if the technology existed, which it does not. The honest answer about TRAPPIST-1 is that it is not a destination for this century, or probably the next several. Unless propulsion physics undergoes a breakthrough that is currently impossible to foresee, sending human beings to TRAPPIST-1 requires a civilization-level multi-generational commitment to a voyage that will outlast every institution that sends it. Whether that commitment is worth making depends on what we believe about the value of expanding beyond our star. It is not a scientific question. It is a philosophical one. The physical environment of interstellar space is not simply empty. It is not just the void between stars. It is an environment filled with hazards that most discussions of interstellar travel mention briefly, if at all. But that any serious mission architect has to contend with as central engineering challenges. The most serious of these is radiation. In interstellar space, far from any star's magnetic field and far from Earth's protective magnetosphere, a spacecraft is exposed to cosmic rays. Cosmic rays are high-energy particles, protons, helium nuclei, and heavier atomic nuclei that travel through the galaxy at nearly the speed of light. They originate from supernovae, from neutron stars, from active galactic nuclei. They arrive continuously from all directions, carrying energies that exceed anything particle accelerators on Earth can produce. Inside the protective bubble of our solar system, Earth's magnetic field deflects the lower energy cosmic rays. Our atmosphere absorbs those that get through. Humans at the Earth's surface receive about a millisievert of radiation per year from cosmic sources, a dose considered essentially harmless. In deep space, beyond the sun's magnetic protection, the dose rate for cosmic ray radiation is roughly 200 to 300 millisieverts per year. That is a significant chronic radiation exposure. Over a 42-year journey to Proxima Centauri, even ignoring all other radiation sources, a crew member would accumulate a total cosmic ray dose approaching 10 sieverts. For context, a dose of 4 to 5 sieverts, received acutely, has a 50% chance of being lethal without medical treatment. Received slowly over decades, the same total dose causes elevated cancer risk, neurological damage, and accelerated aging rather than acute radiation syndrome. But the long-term health consequences of decades of elevated cosmic ray exposure remain incompletely understood. There are no long-term human studies, because no human has ever been exposed this way. Astronauts on the International Space Station receive elevated radiation compared to Earth's surface, but they are still within the Sun's protective magnetic field. The crew of an interstellar mission would be in a categorically more hostile radiation environment than any astronaut has ever experienced. Shielding helps. Thick materials, water, polyethylene, aluminum absorb or deflect some cosmic ray particles. The most effective approach is to surround the crew habitat with water tanks, which serve double duty as radiation shielding and water supply. But heavy nuclei in cosmic rays are particularly difficult to stop. When these particles collide with shielding material, they can produce secondary particle showers, fragments of the collision that themselves carry significant energy. In some configurations, thick shielding can paradoxically increase the crew's total radiation dose by producing these secondary showers. There is no simple solution. Shielding helps and is necessary, but it cannot eliminate the radiation environment entirely. Crew rotation. Spending some proportion of the day in the most heavily shielded areas of the ship can reduce effective dose. Active shielding concepts, using strong magnetic fields generated by superconducting coils to deflect charged particles, have been studied. They could be effective for cosmic rays, which are all charged particles. But the technical challenges of maintaining superconducting magnets reliably for decades in the interstellar environment are significant. The radiation environment is not a mission-ending problem, but it is a real and serious engineering challenge that affects crew health across multi-decade voyages, and that requires active design choices in every aspect of the ship's layout and operation. Beyond radiation, the interstellar medium itself presents hazards that increase dramatically with speed. The space between stars is not perfectly empty. It contains gas, mostly hydrogen, and helium at extremely low density. In the local interstellar medium near our solar system, the average density is roughly 1 atom per cubic centimeter. That sounds like nothing. And at the speeds of current spacecraft, it is essentially nothing. Voyager 1 has been traveling through the interstellar medium for over a decade, and the gas density there is completely irrelevant to its operation. But at 10% of the speed of light, the situation changes. A spacecraft moving at 18.6 million miles per hour is encountering each atom of gas not as a stationary obstacle, but as a projectile, striking the ship at that relative velocity. Each collision transfers a tiny amount of energy. Accumulated over years of travel, those collisions create measurable drag. They erode materials. They contribute to the ship's radiation dose. More critically, the interstellar medium also contains dust grains, solid particles ranging from nanometers to micrometers in size. A dust grain, 1 micrometer across, traveling at 10% of light speed relative to the ship, hits with a kinetic energy roughly equivalent to a rifle bullet. Not from the grain's own speed, the grain is essentially stationary. From the ship's speed relative to the grain. The ship drives into the grain at 18 million miles per hour. The result is the same as if the grain hit the ship at that speed. At 5% of light speed, a millimeter-scale grain of sand, not unusual for interstellar space, would hit a spacecraft with energy comparable to a small explosive charge. At 20% of light speed, the same grain delivers energy comparable to a significant artillery shell. This is not hypothetical. It is a straightforward application of kinetic energy physics. The interstellar medium is not measured in standard deviations of cleanliness. Dust grains exist in concentrations that, over years of travel at significant fractions of light speed, would bombard the ship's leading edge continuously. The engineering solution is a massive forward shield, a thick layer of material at the very front of the spacecraft, designed to absorb impacts and erode gradually rather than allowing them to penetrate to the inhabited sections. This shield must be engineered to last the duration of the voyage, which means it must be thick enough to absorb the total accumulated mass of interstellar material encountered at the mission's speed over its full duration. Estimates for the required shield mass for a crewed mission at 10% of light speed to Proxima Centauri run into hundreds of metric tons. That is a significant fraction of the spacecraft's total mass budget. And the shield has to be in front, which means it has to be launched with the spacecraft, which means all that mass has to be accelerated to interstellar speeds, which requires more fuel. The rocket equation compounds the problem, as it always does. There have been proposals for alternative shield designs that reduce mass requirements using magnetic fields to deflect dust, using ablative materials that sacrifice surface layers to protect the structure behind, using the propellant itself as forward mass. None of these are fully solved engineering problems. All of them require significant development beyond current technology. The interstellar medium is not an afterthought in mission design. It is a central constraint. Communication across interstellar distances presents a challenge that is independent of propulsion and that has no engineering solution in any conventional sense. Radio waves travel at the speed of light. Nothing travels faster than light. Therefore, communication between an interstellar spacecraft and Earth cannot happen faster than the speed of light allows. From Proxima Centauri, that delay is 4.24 years each way. A round trip for any communication is 8.5 years minimum. If something goes wrong on the ship, Mission Control on Earth hears about it 4 years after it happened. Their response reaches the ship 8 years after the incident. Whatever decision the crew faces in that moment, they face alone. They have to resolve it themselves, using the resources available and the knowledge aboard, without any real-time input from anyone outside. This requirement for complete autonomy is so total that it redefines what a mission crew even means. Every interstellar crew, from the first moment, they are beyond communication delay. That matters beyond the point where real-time consultation with Earth is practical, is effectively an independent civilization. They carry Earth's knowledge. They carry Earth's values and procedures and technical expertise. But they make their own decisions. They solve their own problems. They govern themselves by whatever rules they brought with them or develop in transit. Earth can offer guidance 4 years late. The ship acts now. Over the course of a 42-year voyage, the crew would exchange roughly 5 sets of correspondence with Earth, each individual sending a message, waiting 4 years for delivery, waiting for Earth to respond, waiting 4 more years for the response to arrive. You send a question at the start of the mission. The answer arrives roughly 9 years later. By then, the situation that prompted the question has long since resolved itself one way or another. This is not dialogue. It is archaeology. The crew reading Earth's messages is reading responses to a version of themselves that no longer exists in any current sense. And as the journey progresses and the relationship between ship and Earth attenuates over time, the crew necessarily develops its own identity, its own culture, its own priorities, which may or may not remain aligned with the priorities of the civilization that launched them. A multi-generational mission compounds this further. The third generation of passengers aboard a generation ship heading for Trappist. One has never spoken to anyone on Earth in real time, has never received a message from Earth that wasn't 8 years old by the time it arrived, has grown up in a community that is, by every practical measure, independent of Earth in all day-to-day matters. Their connection to Earth is historical, genealogical, a story told by elders about a place no one aboard has seen. This is not necessarily a problem. It may simply be the natural consequence of what interstellar travel means, that you leave, and in leaving, you become something new. But it is worth being clear-eyed about. The first interstellar mission will not be a mission in the way we currently understand that word. It will be the founding of a civilization that begins as an expedition and becomes a culture somewhere in the void between stars. The question of what arrival actually looks like is one that tends to be glossed over in discussions of interstellar travel because it is both the most exciting part and the most uncertain. You have traveled for decades. You have crossed 25 trillion miles. The star that has been your destination for your entire voyage, or for the entire history of your people's voyage, is finally close enough to see as a disk rather than a point. What do you find? For Proxima Centauri, the analysis suggests caution. The star is active. Its flares are intense. Proxima b orbits close, in permanent tidal lock, one face baked and one face frozen. The planet may have an atmosphere. It may have liquid water somewhere, perhaps in the narrow zone between day and night. It may be barren. It may have life. We genuinely don't know. The uncertainty is real. After 42 years of travel, after everything it took to get there, the crew would arrive at a destination that might be welcoming, or might be a radiation-blasted rock with no atmosphere and no water. There is no guarantee. No way to know before arrival. You commit to the journey with the best information you have, and you learn the rest when you get there. For TRAPPIST-1, the scientific case for hoping is stronger. Multiple potentially habitable worlds, the statistics of having 3 in the habitable zone simultaneously, the extended observations will have accumulated by then from Earth. But the same fundamental uncertainty applies. 40 light-years is far enough that even our best telescopes cannot resolve surface features on TRAPPIST-1's planets. We can constrain their size and mass and atmospheric composition in broad strokes. We cannot know if they are alive. Arrival at another star system would be among the most extraordinary moments in the history of our species. And it would also be intensely practical. You have a ship that has been running for decades. Systems have aged. Consumables have been used. The crew has been in a closed environment for a human generation. And now they are in orbit around an alien star, studying worlds they have spent their lives traveling toward, with limited supplies and no backup available for years. The science would be extraordinary. The logistics would be brutal. The emotion of it being the first human beings at another sun would be something no language we currently have adequately describes. That moment will come. Not soon. Not easily. But given what our species has demonstrated about its capacity to solve seemingly impossible problems when the motivation is strong enough, the probability of it never coming at all seems low. The nearest stars are waiting. They have always been waiting. They will continue to wait for as long as it takes. The decision to volunteer for an interstellar mission is unlike any decision in the existing catalogue of human choices. It is not like joining the military, where the risk of not returning is real, but the expectation is that you come home. It is not like a long research expedition to Antarctica or a years-long submarine deployment, where isolation is profound but finite, and you know the date. You'll see sunlight and open air again. It is not even like the early space missions, where the danger was extreme, but the journey was measured in days, and the Earth was never more than 250,000 miles away. An interstellar mission is a commitment to leave permanently. Not in the sense that you couldn't physically return, but in the sense that the world you return to, if you return, will be so different from the world you left that the word return becomes philosophically ambiguous. You go back to the same planet. You do not go back to the same world. The relationships, the context, the shared history, the people who knew you and cared about you and would have wanted to know what happened to you, all of that will have changed beyond recognition in the time you were gone. For a 42-year voyage to Proxima Centauri at 10% of light speed, someone who departs at 30 and returns at 72 comes back to an Earth where their children, if they had any, before leaving, are in their 40s. Their parents are in their 70s. Some of the most important people in their life are gone. The cultural moment that shaped them, the music they grew up with, the political events that felt urgent, the technological landscape that defined their working life is historical. People study it. They don't live it. For a mission to Trappist, one at 10% of light speed, with a return journey included, the traveler returns 400 years after departure. The language has changed. The institutions are unrecognizable. The people who launched the mission are ancient history. The traveler is, in every meaningful sense, a person from the past arriving in the far future. Who volunteers for this? The question is not rhetorical. History offers examples. The first Europeans who crossed the Atlantic in the 15th and 16th centuries knew many of them would not return. Some of them didn't. The ones who did sometimes came back to a world that had moved on, where their absence had been noted and then absorbed, where life had continued without them, where their stories of what they'd seen were received with a mixture of fascination and the practical indifference of people who had their own immediate concerns. The explorers kept going anyway. The settlers who crossed North America in wagon trains in the 19th century knew they might never return to the places they came from. Many of them didn't. They went anyway. The Polynesians, who launched into the Pacific Ocean in outrigger canoes, navigating by stars and wave patterns across thousands of miles of open water toward islands they'd only heard rumors about, knew the journey might end with the sea taking them, or with arrival at an unknown world. They went, anyway. There is something in our species, not in all of us, but in enough of us that is capable of making this kind of choice, of accepting permanent departure as the cost of going somewhere genuinely new. The first interstellar crew will be the most extreme expression of that quality in the history of our species. They will leave, knowing they are leaving. They will depart, understanding that coming home means something different from anything that phrase has ever meant before. And they will go anyway, because they are the kind of people who cannot not go, who look at 25 trillion miles and see not an obstacle, but a direction, who look at 40 years of transit and see not a price, but an adventure of a scope that no human being has ever had the opportunity to experience. The people who will make the first interstellar voyage are probably alive today. They are children, maybe, young adults, growing up in a world where the idea of going to another star is still firmly in the category of someday, rather than soon. They don't know yet what they are, what they will become, what they will eventually choose. But the physics is not waiting for them. The stars are not waiting for them. The distances are fixed. The technology is being built, slowly, by people who came before them. And when the technology is ready, whenever that is, there will be people standing at the edge of the solar system saying, yes. There is something worth understanding about why TRAPPIST-1, despite its brutal distance, occupies such a singular place in the imagination of everyone who thinks seriously about the future of our species. It is not the distance that matters. It is what the science says is there. 7 Earth-sized planets, at least 3 of them in the habitable zone. Astronomers have now been able to study the TRAPPIST-1 system in some detail using the James Webb Space Telescope and other instruments. The picture that has emerged is mixed, but not discouraging. Some of the inner planets appear to lack significant atmospheres, baked clean by radiation and tidal heating over billions of years of close orbiting. But the outer habitable zone planets, particularly TRAPPIST-1E and F, show no clear evidence of the hydrogen-rich atmospheres that would indicate they are definitively inhospitable. They might be rocky worlds with dense nitrogen or carbon dioxide atmospheres. They might retain water. They might, conceivably, bear life. We cannot know from here. The James Webb Space Telescope can measure which wavelengths of starlight are absorbed when a planet passes in front of its star, a technique that reveals the presence of certain atmospheric chemicals. But detecting biosignatures, the specific chemical combinations that life produces from 40 light-years away, is at or beyond the limits of what current or planned technology can accomplish. We may be able to narrow the possibilities with future telescopes. We may be able to rule some planets in or out as habitable. But definitively knowing whether life exists in the TRAPPIST-1 system from Earth is probably not achievable with any foreseeable instrument. The only way to know for certain is to go, which is what makes TRAPPIST-1 both the most compelling and the most cruelly distant major target in the known sky. The most Earth-like collection of worlds we've found, separated from us by 40 light-years and a journey of centuries. The universe seems deliberately difficult sometimes. It is not. It is just large and indifferent to our impatience. there is a version of the interstellar future that is worth holding clearly in mind. Not as a prediction, not as a guarantee, as a genuine possibility, one that the physics permits and the trajectory of human technological development makes plausible over a long enough time horizon. Sometime in the latter half of this century, commercial fusion energy becomes real. The first fusion power plants connect to electrical grids. The physics, understood for decades, is finally matched by engineering capable of making it practical at scale. The implications extend rapidly beyond electricity generation. Engineers who spent careers learning to build, maintain, and operate fusion reactors begin applying that knowledge to compact versions for aerospace applications. Not immediately. Interstellar applications. First, propulsion for missions within the solar system. Mars in weeks instead of months. The outer planets in months instead of years. A practical, operational presence throughout the solar system for the first time in human history. As compact fusion propulsion matures, the design studies for genuinely interstellar applications become engineering exercises rather than theoretical papers. The numbers work. The physics is proven. The question shifts from can we to will we. Sometime in the 22nd century, it is impossible to be more specific than that. A mission architecture for a crewed probe to Proxima Centauri exists on paper that is technically achievable. Not cheap, not easy, but achievable. The decision to actually build it is not a scientific decision. It is a civilizational one. It requires a level of political and economic commitment that dwarfs anything in human history. The Manhattan Project, at its peak, consumed roughly 2% of United States GDP. The Apollo program, at its peak, consumed roughly 4%. An interstellar mission would likely require a sustained commitment over decades that exceeds both of those, probably by a wide margin. And unlike those programs, the return is measured not in years, but in generations. No one who funds the mission will live to see it succeed. No politician who commits to it will receive electoral credit for the outcome. The only motivation is the mission itself. The desire to know. The conviction that reaching another star matters enough to pay the price in resources, in time, in the lives of the people who go. Whether human civilization will ever develop that conviction at that scale remains genuinely uncertain. There are reasons for pessimism. Human institutions are notoriously poor at long-term thinking and at making investments whose returns arrive in centuries rather than election cycles. The challenges of the 21st century climate, inequality, conflict, the disruptions of accelerating technology may absorb so much attention and resources that interstellar ambitions remain perpetually deferred. There are also reasons for something less than pessimism. The track record of our species at solving problems that once seemed impossible is not zero. It is remarkable. And the drive to know what is over the next horizon, which is what interstellar travel is, in its most basic terms, is not a peripheral human motivation. It is one of the most central ones. That drive has not diminished as our knowledge has grown. It has, if anything, intensified. The more we know about the universe, the more clearly we see that there is more to know. And some of that more is 40 light-years away, orbiting a dim red star, waiting. There is a reality about this moment in history that deserves explicit acknowledgement. Right now, in 2026, humanity has no propulsion technology capable of reaching any of these stars in less than tens of thousands of years. We have no technology in active development that changes that in any fundamental way. We have concepts. Fusion drives, nuclear pulse propulsion, laser lightsails. Some of these are feasible in principle. Some have been demonstrated to work in their basic physics. None are funded at the level required to actually build the interstellar-capable versions. Breakthrough Starshot has continued research and development and remains the most actively funded project specifically focused on reaching another star system. Their target is narrow gram-scale probes on flyby trajectories, but the target is real, and the funding is real, and the physics works. Fusion research has accelerated dramatically in the last decade, driven partly by government programs like ITER and partly by private investment from companies like Commonwealth Fusion Systems and TAE Technologies, who are pursuing commercial fusion energy on timescales of years rather than decades. If commercial fusion becomes real, the technology base for fusion propulsion follows as a natural development. The timeline from commercial fusion power to fusion-propelled spacecraft is long. But the path is not invisible. Nuclear propulsion for spacecraft is also seeing renewed interest. NASA and the Defense Advanced Research Projects Agency announced a joint program called Draco Demonstration Rocket for Agile Cislunar Operations to develop and test a nuclear thermal rocket in orbit. The stated timeline envisions a test flight before the end of this decade. Nuclear thermal propulsion is not sufficient for interstellar travel, but it is the first step in establishing the broader nuclear propulsion technology base, the engineers, the regulatory frameworks, the operational experience that more capable future systems would require. Progress is real. It is just slow relative to the scale of the problem. The gap between where we are and where we need to be is not a gap that closes in a decade. It probably doesn't close in a century. But it may close in 2 or 3. And in the context of the stars which have been burning for billions of years and will continue burning for billions more, 2 or 3 centuries is nothing. It is worth considering what actually needs to be true for a crewed interstellar mission to ever happen. Not the technical requirements, which we've covered, the human requirements. Someone has to decide to go. That sounds trivial. It is not. A crewed mission to Proxima Centauri, even with mature fusion propulsion, commits the crew to 40 or more years away from Earth. The crew members who volunteer know, when they board, that they will not return to the world they are leaving. They will return to Earth, in principle. But the Earth they return to will be 40 to 80 years older than the one they departed from. Everyone they knew, personally, will be old or gone. Whatever cultural moment, they were part of the music, the politics, the conversation, the shared references, will be historical. They will be strangers in a world that will have moved on without them. And that is the optimistic scenario, the one where the mission succeeds, where everyone survives, where the propulsion works and the life support holds, and no medical emergency ends the voyage. In the less optimistic scenario, they don't come back at all. Not because of catastrophe, necessarily. Simply because there is no compelling reason to make the return journey after 40 years at another star. The mission is to go and to be there. The return is optional. And returning to an Earth where everyone you knew is old or gone is a reason that many people, having spent 4 decades adapting to life at another star, might choose not to bother. The first interstellar travelers will be, in some meaningful sense, the last of their kind. The last human beings who are fully of Earth in a way that no one who comes after them will be. They will launch from a world they know. They will arrive at a world no human has ever seen. And everything in between, the decades of transit, the adaptation to another star's light, the daily reality of a sky that contains a different sun will make them something new. Not inhuman, not alien, but different. Star people. People who chose the hardest journey our species has ever contemplated and made it. The question of who those people will be is not fully answerable now. But history suggests they will be people who share a quality that has driven human exploration at every scale. The inability to be satisfied with knowing something exists without seeing it. The ability to say, the numbers are terrible, and the distance is enormous, and the risk is real, and I'm going anyway. That quality is not rare. It is not exclusive to heroes or exceptional individuals. It is present in ordinary people who make extraordinary choices. The crews of the first ships to cross the Pacific had it. The people who crossed land bridges into unknown continents tens of thousands of years ago had it. The astronauts who climbed into rockets in the 1960s and went to the moon had it. The engineers who will eventually build the first fusion drive, and the mission planners who will design the first interstellar mission, and the crew members who will volunteer for it, have it too. They just don't know yet that that is what they are. There is one more thing worth saying about all of this. About the distances, the timescales, the physics that seems designed to keep us here. The nearest star beyond our sun is 4.24 light-years away. 25 trillion miles. It has been there for billions of years. It was there before the first life appeared on Earth, before the continents took their current shapes, before the sun itself existed, and for the entire duration of our species' presence on Earth. Every human being who ever lived, every civilization that rose and fell, every generation that looked up at the sky and tried to make sense of what they saw those stars have been burning in the same sky. We have spent the better part of our civilizational history not knowing what stars even were, not knowing they were suns, not knowing they had planets, not knowing that some of those planets might harbor conditions similar to the ones that made life possible here. We have known those things for a very short time. And in that very short time, we've already crossed from wondering what's out there to measuring the atmospheres of planets orbiting other stars. From thinking the stars were lights fixed to a celestial sphere to sending probes into the space between them. From believing Earth was the center of everything to understanding that it is one of at least several 100 billion planets in this galaxy alone, orbiting one of at least several 100 billion stars. The trajectory of that knowledge, if you trace it honestly, is not one that leads to permanent confinement. It is one that leads outward, slowly, painfully, slowly, by the measure of any individual human life, but relentlessly outward, by the measure of what our species does when confronted with problems this hard. We don't solve them immediately. We don't solve them easily. We spend centuries working on them, making incremental progress, losing threads and picking them up again, arguing about priority and funding and approaches. And then one day, we look up and realize we've actually gotten there. Not where we imagined we would be. Not in the way we expected. But there, farther than before. The stars are not going anywhere. They don't need to. They will still be burning in the same places they have always been, surrounded by their planets, waiting with the patience of physics. Long after every person alive today is gone, and long after the civilizations those people built have become whatever comes next. The question is not whether our species will ever leave this solar system. Physics does not say no. The universe does not forbid it. The distances are brutal, and the timescales are long, and the engineering is not done, and the social challenges are not solved. But none of those things say never. They say not yet. And not yet carries within it the assumption that this is a species that continues, that keeps building, that tolerates the gap between where we are and where we need to be long enough to close it. Every star in the sky tonight has been there for as long as humans have been capable of wondering about them. 25 trillion miles to the nearest one. 235 trillion miles to the most compelling planetary system we know of. The numbers are what they are. The physics is what it is. And somewhere in the future of this species, if there is a future, someone is going to cross that distance. They are going to look back and see the sun, our sun, as a point of light in a sky full of points of light. And they are going to be somewhere new, for the first time in the history of life on this planet. Somewhere genuinely, irreversibly new. Good night.